All right, here we are for Honors Physics Free Fall Questions and Problem Set. We're taking a look at problem number 4. A kangaroo jumps to a vertical height of 2.7 meters. How long was it in the air before returning to Earth? So I'm going to go ahead and draw a little quick sketch. And we'll say... Right? And let's see, can I draw a kangaroo? That's a good question. So he's going to have great big hoppy type feet, right? And body and arms kind of like this, right? And let's see, its head, it's got almost like rabbit ears, doesn't it? They're smaller. I bet those ears are too big for a... But yeah, I think kangaroo looks something like that. Anyway, so let's see here. So the kangaroo is going to jump up in the air, and we know that it's going to hop up 2.7 meters. And the question is, what's the amount of time that it was in the air before returning to Earth? And that means we want to know the time for it to start here on the Earth, say, and go up, and then come back down. So we're going to go from the ground to the ground here. So let's list out our, let's go ahead and list out our motion variables, our kinematics variables. A, V naught, V, displacement, and time. And you say, all right, we know that once the kangaroo leaves contact with the ground, the only force acting on it will be gravity. And so we can say the acceleration. And again, I'm going to go ahead and label my coordinate axes, and I'm going to choose to call up positive, down negative. And so we know the acceleration is going to be a negative 9.8 meters per second squared. Let's see here. Do we know the launch speed? No, we don't know how fast it's going when it takes off. Do we know how fast it's going when it comes back down? No. We know it'll be equal but opposite to the takeoff speed, but that's all we know. The displacement, well, it starts here and it ends here. So the change, the overall change is going to be 0. And then do we know the time? And you say, oh, no, we don't. Like, uh-oh, we only know 2 variables for this motion. You say, well, what about this 2.7 meters? We didn't use that. Well, that's the displacement from here to the peak. So what I'm going to need to do is, instead of looking at the total motion, we want to know the total time, but we're going to make use of the fact that we know that for a motion like this, where it goes up and returns to the same height, we know that the time to the peak is half the total time. So instead of going from here, hop, back to there, instead of doing that, we're going to do a calculation from hop to the peak. And then we'll go ahead and we'll just take that time to the peak and double it. And that'll be the total time up and down. So I'm going to go ahead, I'm going to make a new chart. A, V naught, V, displacement, and time. And this is going to be ground to peak. Whereas this first one over here, this chart was for ground to ground. And I just did not have enough information to solve that yet. So I need to go ground to peak, make use of the fact that we know the height to the peak is 2.7. We're going to use that information to help us solve. So filling out this chart, we do know the acceleration is, again, still negative 9.8 meters per second squared. That's the acceleration when the only force acting on you is gravity and you're near the surface of the Earth. The initial velocity, we don't know. The final velocity, you say, oh, wait a second. If we go up to the peak, we know the velocity at the peak is 0. We discussed that last couple problems. And so that is it. I'm sorry, I just filled in the wrong space, didn't I? The velocity at the peak, that's our ending velocity. We're going from here to here. Is 0 meters per second. Our takeoff speed, we don't know what that is. This is where I use a little bit of whiteout. That's where whiteout comes into play. Oopsie doodles. There we go. All right. Let's see, displacement from here to the peak, that's that 2.7 meters. We can make use of that fact. They gave us, and the time to the peak we don't know, but if we can solve for that time to the peak, we're going to be able to double it and get the total time. So that's the plan. So I take a look at this and you say, okay, we've got A, we got V, we got delta X, we got T they're looking for. Do we have a formula that has just those 4 variables? And if you take a look at the formulas that we have, you will be slightly disappointed. You say, the formulas we have, V is AT plus V naught. V squared is V naught squared plus 2A delta X. And displacement is V naught T plus 1/2 AT squared. And you say, this one is missing delta X. We want one that's missing V naught. This one is missing time, and this one's missing V final. And you're like, oh, you've got to be kidding me. Well, there's another option, and that is, instead of looking at the motion from here to the peak, why don't we just look at the motion from the peak back down? Do you see what I'm saying? So I'm going to flip this. Instead of going ground to peak, I'm going to go peak to ground. Now my acceleration is still downward, right? Gravity still pulls downward on it. It's going to get slower as it goes up. So the acceleration must be opposite the velocity. That's still going down. But now we're going to start at the peak and go down to here. We're going to look at it as he's falling back down that 2.7 meters. So the V naught is going to be 0. See, I was right the first time. The V naught is going to be 0. The final velocity as he hits the ground, we don't know that one. The delta X is going to be, now we're going down, negative 2.7 meters. And the time's what we're going to find. So now I have A, V naught, delta X, and T. I want the formula that doesn't have V. That will be this one. This one will now work swimmingly. And so that's the one we're going to use. Okay, because we decided to go from the peak to the ground. We'll find the time there, then we'll double it. That'll be the total time for up and down. So we're going to find the time to go down. So here we go. Finding that time. You look at it and you say, once again, this is a formula that has a constant term, t to the first, t to the second. Are we going to have to solve a quadratic? Fortunately, no, because V naught is 0. And so that means this term will drop out nicely. We won't have to solve a quadratic after all. See here. So if I can see ahead of time that that V naught term is going to cancel, I'm just going to go ahead and take care of that now. I'm trying to solve for t. So now I have just displacement is 1/2 AT squared. Let's get the t by itself. Move the 2, multiply by 2, divide by a, take a square root. So I can see that I will have 2 times the displacement divided by the acceleration, take a square root, and that will be my time. And so put in my values, square root 2 times, my displacement was a negative 2.7. You ever get nervous when you put a negative under a radical? Fortunately, the acceleration is another negative, negative 9.8. So those two negatives are going to cancel each other out. Shoo! We'll get a positive. We can take the square root. And this is where I reach for my calculator. And we say 2 times 2.7 divided by 9.8. Okay. And we get 0.551 seconds. You say, well, hang on, that's just the time for this to go from the peak to the ground. To find the total time it's in the air, we're going to double it. And so when I double it, you say 1.102 seconds is the hang time for that kangaroo. Ta-da! And that's that problem. Are there other ways of solving it? Yeah, we could. Like the hiccup we had here was that we didn't have a formula that had A, V, delta X, and T, and didn't have V naught. We could have derived a formula that had those 4 variables if we wanted to. We could have taken these, maybe say, these 2 formulas, perhaps, and we could have isolated V naught in one of them, and then substitute in the other one where it says V naught. And we would get rid of the V naught term that way. And we'd have an equation that just had the variables we wanted. So we could have done that. But I don't know. I enjoyed like choosing my my setup and choosing different starting conditions, going from different spot to different spot. I think that was nice. All right, that's it for problem 4. All right. So it was pointed out to me that when I went ahead and did this calculation down here for the kangaroo, that I accidentally forgot to evaluate the radical. So I multiplied this out and divided it out, and negatives canceled, but then I forgot to take the square root, actually. So I need to take the square root of 0.551. And when you do that, then actually this value comes out to be 0.742. Let me take the square root of 0.551. And then I need to double that because we want the time to go up and down. And so when you do that, the answer that you get out is 1.4, we'll round it off to 1.48 seconds. Okay, and so that's the hang time for a kangaroo is 1.48 seconds. All right. Thank you, Miss Thomas, for pointing that out. Okay, so there you go. Oh, and not quite as important, but it occurred to me later that what my kangaroo was missing was a tail. There, that's a better kangaroo. All right, glad we got that straight.